Okay, in this video, I'm going to split it up into a couple of parts, but I'm going to go through essentially kinematics chapter 10. Because the majority of you have done physics, I'm going to expect that you know how to do this question. We've got a velocity time graph. And of course we've got a car and a truck travelling at different speeds, and of course you might have one passing the other, etc. Now, can I just get you to have a go at this question? It's a short answer question from an old 2002 exam. I'm going to pause the video now, have a go at it, and I'm going to give you 5 minutes. Go. All right, now first of all, it's saying find t, and at time t, what is time t? Like, it just says a car travelling at 24 meters per second overtakes a truck, yada yada yada, at a constant speed 7 meters per second along a straight road. T seconds later, the car decelerates uniformly at rest. The truck continues at a constant speed. So what I'm going to do is I'm just going to work out that the area under the graph, the area under my VT graph, gives me what? The distance, gives the distance travelled. Okay? Now, what about the distance of the truck? How far does the truck travel? 17 times 60, I reckon that's 1,020. Is that right? 1,020 what? Meters. Okay. Now, what about, though, the area? So we've worked out the truck. We've worked out that area, or that distance of the truck is 1,020 metres. The truck continues at a constant speed. Yeah, this is exactly 60 seconds after the car has passed. Can't you say that t plus 60 over 2 times 24, what's that going to give you? What's that going to give you? The area of the triangle? Area of the trapezium, isn't it? Area of the trapezium. Now you can do it the few other ways, but I just did that. This is a trapezium. A plus B times height over 2, yeah? Okay with that? Now I'm going to work that out to be, well actually, you know what? I'm there. Well, the area of the trapezium is what? Is equal to what? It has to be equal to 1,020, doesn't it? Is that right? So now I'm going to do a little bit of this. 24 divided by 2 is 12. 12. So I'm going to get 12 on the other side. 12 times, so that's 12,240. T plus 60. Is that, no, sorry. 12, I've got to divide it by 12, duh. So t plus 60 is equal to 85, yeah. Now, therefore, t is equal to 85, take 60, which is 25 seconds. Did we get that? Okay, very good. Now, that's area under graphs and things like that. The area under a velocity time graph, and remember, if you forget, meters per second times seconds is equal to meters. Okay. Now, this time, a ball is dropped from a concrete floor. Have a go at this. I'm going to give you a minute to have a go at this, please. Because you're physics students, most of you. Shh. Okay, so this question. Shh. First of all, it says the ball is dropped from rest to a concrete floor. So given this is a VT graph, that instantly means that this velocity, if it's dropped from rest, so it's not A, and it's not B. Bounces vertically to half its drop height. Now, the acceleration of gravity is equal to 9.8 meters per second squared, which is the same as 9.8 meters per second. So, and this is why if you fall off a 15-meter tall roof, okay, your acceleration, you're going to be going pretty fast. By the time, think about it, after 1 second, how fast will you be going? After 1 second, you will be falling at 9.8 meters per second.
That's like almost Usain Bolt's speed.
Yes, that is Usain. Well done. I love these little interesting things. Can you just say that? Can you just say that, Lachlan, to the camera? Lachlan, can you say that?
It's almost Usain Bolt speed when he runs.
Good, because I believe Usain Bolt's record is 9.67 seconds. He actually beat that. 9.58. Sorry.
It's such a great maths video.
Okay, now, Usain Bolt, 9.8 meters per second. All right, but therefore, what about if I was falling for 2 seconds? What would be my speed? 19.6 meters per second, which is bloody fast. Okay, but what happens if I fell off a 35-meter tall roof?
Oh, you're in trouble there.
You're
bloody fast.
That's right. Now, all right. Shh. Now we've got to think about it. If it goes half, you've got to think about this question. Half its drop height. It means that, well, for starters, what happens is when the ball is dropped and it goes whee, then this velocity we're going to call this velocity positive. We're going to call down positive. We can do that. But then when it goes back up, it's then all of a sudden, as soon as it hits the ground, it's going to go from positive to negative. So this thing here is absolutely baloney because it needs to go from positive to negative. So we've instantly ruled out these. Now, the height. If you have a look at this question here, if I was to do a velocity time graph, work out the area there and the area there, that to me doesn't look like a half. So I reckon that the only answer is A. Oh, sorry, C. Okay? The answer's C. Okay? You okay with that? All right, now I'm going to show you the next one. Shh. A particle moves with a constant acceleration in a straight line. I'm going to get you to have a go. Yeah, no, we'll just do that one. Have a go at this one and I'll give you a couple of minutes. Thank you. Shh. All right, now your formula sheet. Of course, you've got areas of trapeziums and all of that sort of stuff, ellipses, hyperbolas, all of your circular functions. We've done all of this stuff. Remember, if you have to find the domain and range or implied domain and range of an inverse function, you can do so using that formula sheet. We know that the derivative of sine, cos, tan and all of that sort of thing, that's not on there, but product and quotient and chain rule, Euler's method, which we went through in differential equations, acceleration. Look at that, ladies and gentlemen. Look at that. Now, shh. First of all, how do I like start drawing on this? Like, I don't know. Shh. Just stay here for a second. Shh. So, acceleration. We need to know what these expressions are. If you think about it, if I have x as a function of t, x as a function of t is just like my position. If I derive that twice, I get the acceleration. The acceleration is also, if you think about it, final minus initial velocity, change in velocity, dv, dt. Does that make sense? And now, V dv dx, I'd like someone to work that out during the break and tell me where that came from and where this d by dx of a half v squared is, because this stuff is what you need to know. This is essentially the hardest part of kinematics, is knowing which one of those to use under which circumstance. Now, of course, then you've got your uniform acceleration. Now, can I make this 100% clear? The word uniform, if an acceleration is changing, and a lot of the time it is, we're using these, you cannot use the constant acceleration formulas. Does that make sense? Okay, I'm going to say it again. Do not use the constant acceleration formulas. V equals u plus at, s equals ut plus half at squared, v squared equals u squared plus 2as, and then there's the other one which is basically just derived from the other three. Because if you're doing that, you don't understand physics. All right, I'm going to give you just a 2-minute breather, okay, and then we'll get, that's part 1 of kinematics, okay? Part 1 of kinematics, and we are going to go through this question when we get back, looking at those formulas. So you make sure you get your formula sheet out. I'm going to stop there.